With an appreciation of the additive and non-additive matrix, now we are ready to understand how to determine and validate feasible routes, which is a primary requirement in various routing protocols and algorithms. In this module, we shall make some network model assumptions that would form the basis for finding the feasible routes. We'll formulate the problem and then we'll see that it turns out to be a multi-commodity problem. And we'll also look at single commodity problem. The reference is Anurag Kumar. The author has emphasized that a single commodity and multi-commodity problem are routing problems in which the source destination pairs try to find out the most optimal path, or we say the most feasible path, that follows certain constraints that we define in the network. Let's look at some of the variables that we shall use. It is important to look at these variables, but this is not an exhaustive list. When you are planning to model and simulate your own network, you may have to extend this network model. Let's start with the network that comprises a certain set of nodes represented by n and number of links as L. This epsilon is the sum of the propagation delays and the maximum transmission time on a link L. C sub L is the available capacity on that link, and K is the total number of source destination pairs in the network. Now, if we consider a path through the network between source and destination pair, that is the two routers on the farthest ends, the capacity on the path P is actually the minimum of all the individual link capacities, because in terms of link capacity, it is a non-additive matrix, and the least of all is the end-to-end capacity of the whole path. The number of hops taken on the path P are represented by HP. If we are implementing the leaky bucket algorithm as traffic, shaper, and flow management system, and sigma sub k is the maximum burst size for the kth flow, and rho sub k is the average rate of the source, the maximum packet length that is belonging to session k is C sub k, because it will have a direct impact on the exhaustion and consumption of the overall channel capacity. Now, let's look at the problem. In order to determine a feasible route, we have to find a path for the source destination pair along the links, that is, the rate which is required by the source destination pair is met, the delay requirements are also satisfied, and the capacity constraints on that path comprising those links should not be violated. Then we can look at the upper bound on the delay as one of the most important requirements to determine the feasible route would be incorporating all these parameters as given by this. For the kth flow, the delay is for a path P, rate R is represented by this. You can see that the expressions on the right hand side are actually giving us the delay, because the first term on the right hand side is the numerator divided by the rate, giving us delay, and the second one is the summation of all the transmission delays on link L summed over the whole path. If all the paths for all the source destination pairs are computed, it is a multi-commodity problem, since there are a very large number of paths available. So multi-commodity problem is very heavy to be computed offline, and it is termed as non-parametric hard problem. But if we are looking at a source destination pair, it is a single commodity problem.